Okay, so we're going to have a look at this as just kind of a quick review of how inclined planes and sort of Newton's second law stuff works in general. Okay, so remember, an inclined plane is an interaction of many forces. Okay, it's an interaction between gravity and the surface of the plane. There can be other forces if the object is being pulled up the ramp, or there's friction involved. There can be those forces as well. This is the simplest example where we just have an object placed on the ramp. Okay, it's going to slide down it because there's no friction. Okay, there's nothing pulling it up the ramp, so it's just going to slide down. Now, they tell us the box is 445 newtons. What did they tell me? They told me the weight. Right, they did not tell me the mass, and for this question, I don't need it. Okay, they just told me that the mass of the box, or sorry, the weight of the box, sorry, is 445 newtons. So the force of gravity is 445 newtons, and gravity always acts straight down. Okay. The other thing we know is that the ramp is angled at 25 degrees. The other force that's involved, since this ramp is frictionless, is the normal force. And the normal force always acts straight out from the surface of the ramp. Okay. If I treat this like it's a vector diagram, these are both drawn tail to head, my resultant would be this line. This is F parallel. It is the net force between normal force and the force of gravity. Okay? So that's the force we're being asked to find. The other thing we have to remember is that normal force, that's this side, and the force of gravity are separated by the same angle that the ramp is inclined. That's why they don't directly oppose each other. Okay? Their difference is 25 degrees. Now that I know the hypotenuse of this triangle, can I find F parallel?
Yes.
Okay, it's the opposite side, so what trig function am I going to use? Sine. Okay, so I'm going to go sine of 25 times the hypotenuse, which they told me was 445 newtons. Okay, that's how I calculate F parallel, in case we've forgotten from last week. Okay, so we're going to go sine of 25 times 445 newtons. So, F parallel, F parallel is 188 newtons. Okay, now, do I need to put a direction on that? Is force a vector quantity? Then I need to put a direction on that. What direction does F parallel always act? Down the ramp. Right. Not down. Down the ramp. They're different. Okay? So 188 newtons down the ramp. Okay. If the question was worded a little differently, maybe it said, there's 20 newtons of friction and an applied force up the ramp of 200 newtons, then I would have other forces involved. Okay? And then I would change this diagram a little bit. I would put F parallel in here, okay, as a free body, as part of the free body diagram, okay, say 188 newtons. Okay? I'd have an applied force of 200 newtons and friction, which I think I said was 20 newtons. Okay? Sorry, friction wouldn't be acting up the ramp in this case. Oh, that was a terrible number to pick because it throws it off completely. Let's just say I said that the force upwards was 300 newtons, because then the question works. See, this is what happens when you pull numbers out of your head. Okay, 300 newtons, okay, and there was 20 newtons worth of friction. Which way is friction acting? Down. It has to be, because friction always acts opposite the movement. The movement in this case is definitely up. There's way more force up than there is down. Okay, so we would have 20 newtons worth of frictional force acting down the ramp. Can I calculate now, like net force, same as we always do? Right, vector sum of all forces, F equals m times a, and we go from there. Right, is that ringing a bell? Okay, so what we're going to work on today are a few different kinds of examples of vector problems to do with Newton's second law, a few more inclined planes, and tomorrow we're going to do our lab. Now, our lab is going to involve a situation like we've talked about already. In fact, why don't we just go over, I'll make up a question, you guys copy it down, that'll be like our lab situation for tomorrow. Okay? Our lab situation for tomorrow is going to involve a pulley. Okay? We're going to have a cart Okay, that'll be here on a level surface. Okay, so the cart will just say has a mass of, I don't know, 1 kilogram, just to be easy. Okay, it's going to be attached by a string over the pulley to a mass that is hanging over the pulley, and we'll say that mass will be 0.5 kilograms. What's going to happen here if I release this system? Okay, the 0.5 kilogram mass is going to drop, and it's going to do what to the cart? Pull it along. Okay. If this is a frictionless system, let's just say it is, because we're going to say that tomorrow our lab is frictionless, even though it's not, but it's pretty close. Okay, let's say this is a frictionless system. I want you to calculate the acceleration the cart would experience. Okay, the acceleration the cart would experience due to this system being released, and this is all the information that you need. Okay, I'm going to give you a couple minutes to think about that one, because I see a few blank looks here, and I think if you think about it for a few minutes, you'll get it. Okay, I'm hearing some stuff in here that's good. I'm hearing like some conversation about, okay, here's some of the forces that are involved. Well, in actual fact, there's only how many forces driving this system? One. Okay, there's only one force driving this system, and it's the force of gravity acting on this mass. Okay, gravity is acting on this mass, but what else is acting on this mass? The table. So what happens to the force of the table and gravity? They're equal. So that doesn't matter. And we already said there's no friction, so there's nothing resisting the movement of this mass. It's just going to roll. Okay? So the only force we have is the force of gravity acting on 1/2 of a kilogram. So we go m times g, 0.5 times 9.81, and we get that the force here is 4.905 newtons. Okay, now here's what we have to remember. Anytime we have two masses that are connected, we're dealing with what kind of a question? A system question. What do we need to remember about system questions? All of the mass is being accelerated by the net force. Now, we already calculated the net force. Okay? As we said, there's only one force acting in this system, and that's it. Therefore, that's the net force. We just did vector sum of all forces in our head because we don't need to do anything else. Okay? So now, we just need to say that F net equals m times a, and then acceleration equals F net divided by m. Okay? And so that's going to be 4.905 divided by our mass of our system, which is 1.5 kilograms. Okay? So when we do that, we should get like 2 point something. 3 point something? Okay. So 4.905 divided by 1.5, okay, gives us 3.27. Now we only have, excuse me, we only have one significant digit. I wouldn't do that on a test. Okay, so we would actually have just 3 meters per second squared, and then what would I have to write on this? Because I asked you for the acceleration of the cart.
Times
Right.
Oh.
Okay? So, it's all these little details that we have to remember. That's why I picked these two questions to start off with. Okay? Because if you over the long weekend, you would probably forget some of these little details. Okay? These are some of those little details we need to remember about certain types of Newton's second law questions. All right? So, you guys are going to need to have out your question package. Sorry, your workbook, sorry. So that's on Google Classroom. You guys can get it there. I'm just going to grab it here. Okay, so on Friday, we started working on this Newton's second law worksheet number 1, and we were doing like the super easy F equals m times a questions to start it off. Okay, we just did question number 23, and then I made up another one. Okay, what I want you guys to try right now are actually ones off of this force as a vector quantity worksheet. Okay, so I want you guys to try question number 1 right now. Okay, and then we'll work through that one together because it's going to involve some vectored forces. Okay, so we got a tow truck pulling a car behind it. Friction is opposing with a force of 500 newtons. The mass of the car is 1,500 kilograms. The cable makes a 45-degree angle with the road and has 2,000 newtons of tension in it. What's the acceleration of the car? Okay, so this involves some vector stuff. Okay, so you have to keep that in mind. Some vector stuff is involved here. The thing you need to remember is the car moves which way?
Forward.
Forwards. It's going to move horizontally forwards. It's not going to move in the direction the cable is pulling. It's going to move horizontally. Okay, so you need to think about that when you're doing this question.
Where do you find this?
So if you go into Google Classroom in the classwork section,
Yeah.
okay, it's in there. It's the dynamics workbook here.
Oh, okay. So
Yeah. Okay, so try number 1 for right now, okay, and then we'll go through that here in a minute. Okay, so remember that force is a vector quantity. The first thing we want to do is draw a free body diagram of this situation. So here's the ground, okay, and here's the car, right? So the car is 1,500 kilograms, okay, and I know the following forces are acting on the car. Friction, directed backwards, okay, gravity, directed downwards, normal force, directed straight upwards. And what happens to these two forces? They're going to cancel each other off. I don't even need to calculate that. Okay? The other force that's acting is this one. Okay? This is the tension in the cable. It's 2,000 newtons. Okay? Now, in actual fact, normal force is actually a bit smaller than the force of gravity. Okay? They don't actually cancel each other off. This is angled, which means it's pulling both horizontally and vertically. Okay? And it's doing so at a 45-degree angle. Now, since the car is moving horizontally, normal force, this vertical component here, and gravity all add up to what? 0. The car is not accelerating vertically. Okay? So we know that all the vertical forces add up to 0. We know the car is going, is going to move horizontally. So that means that the force of friction and this force don't add up to 0. Everyone all right with that? Okay, can I calculate that horizontal force? Yes. Okay, so I'm going to calculate that horizontal force by going cos of 45 times 2,000 newtons. Okay, so our horizontal force is going to be 1,414 newtons. Obviously, with all those decimals, I'm not going to forget about those. Another decimal, 1,414 newtons. Okay, so that's the horizontal force. Okay, I've got the force of friction here that I know is 500 newtons. I know this force, and this force are already taken into account. Okay, they cancel because the car is not moving vertically. So can I calculate the net force now? Yes. Okay, so net force is going to be the vector sum of all forces. I already eliminated ones that added up to 0. I'm only going to be worried about the ones going forward and backward. So 1,414 plus 500, which is negative because it's backwards, or minus 500, whichever way makes more sense to you. Okay, so we're going to have 914 point whatever newtons of net force. Everybody okay with that? Yeah? Okay, can I calculate the acceleration now? Yeah. F net divided by mass. The mass is 1,500 kilograms. So we take our, we subtract our 500 from that. There's our net force. Divide that by the mass of the car. It's going to accelerate at 0.609 meters per second squared to the right or forwards or whichever way it was defined. Okay. Yeah. Yes. All right, everybody okay with that? All right, so sometimes we've got to look at the vectors. Sometimes we're going to do vector addition where we draw them tail to head, and other times we can look at this and go, okay, it's not moving or it's not moving vertically, so that means all the vertical forces cancel. And I'm just looking at horizontal forces. So sometimes you have to read into the question and get the context a little bit. Okay, number 2 is going to involve you doing a vector diagram. So you have a free body diagram, then a vector diagram, tail to head, okay, of the forces involved. I'll give you a few minutes on that one and then we'll walk through it. All right, so number 2 is pretty straightforward, right? Our free body diagram is a diagram of the sled here that is a mass of 90 kilograms. Okay, we have a 400 Newton force and a 400 Newton force, the 2 dogs pulling forwards. Okay, we have a force of friction, 300 Newtons pulling backwards. Calculating our net force is pretty straightforward here. We've got 400 plus 400 is 800 minus 300. Our net force, okay, is 500 Newtons in a forward direction. We can calculate the acceleration then simply by going 500 divided by 90, net force over mass, okay, and that'll give us our positive 5.55 meters per second squared forward. Okay, that one's about as easy, okay, as a vector-related Newton's second law question we get. Okay, because there's no tricks, there's nothing intuitive about it. It's just sum of all forces and m times a. Okay, questions on number 2. Okay, we did some like this one on well, Thursday or Friday of last week. Okay, so we have our sine. Okay. Like this, okay? The sine is a mass of 55 kilograms, okay? These cables are identical. Each one hangs at a 35-degree angle from the buildings. Okay? We want to calculate the tension in each cable. Right? What do we call this kind of question? Static. Right. This is a static question because what is the sine not doing? It's not moving. What's the net force in any situation where something's not moving? 0. Okay, think about that when you're doing this. Let's have a look at this one. I'm just listening to your explanation going, oh man, you were lucky. But that's okay. All right, sometimes better to be lucky than good. So, let's have a look at this one. Okay, there are a number of forces acting here, but they all add up to what? 0. The net force in this question is 0. That's the most important realization you can have about this question. Okay? You can't even start it unless you realize that all the forces add up to 0. So the next step then is to identify all the forces. There is a force of gravity acting downwards on the sine. Okay? We're going to calculate that by going m times g. 55 times 9.81 is going to be what, 539.35? 539.55 newtons. Okay, so there's our force downwards. Now, it's being pulled upwards by 2 forces. What are they? Each cable, right. But here's the thing about each cable. Each cable pulls horizontally and vertically. If the net force is going to be 0, this blue upward force is how much of this black downward force? Half. That's the second realization you have to come to when you're solving this problem. That because there are 2 cables, the upward force that equalizes or cancels out this force is provided by 2 separate entities. So they split it. Okay? So what we have is 539.55 divided by 2. Okay, so 539.55 divided by 2, okay, gives us the vertical force in each cable, 269.775. Whoa. Fly fishing. Okay, where am I at? Calculate. Okay, 269.775. 269.775. Okay, so we've got that. Okay, that's on this side as well. But because the cables are identical, I don't need to calculate it twice. I just need to solve for the tension in this cable because it's identical to this one. All right, now that I have that side and this angle, can I find the tension in the cable? Yep. What side of the triangle am I looking for? The hypotenuse. I have the adjacent side. I'm looking for the hypotenuse. Okay, so to calculate the hypotenuse, I'm going to go 269.775, the adjacent side, okay, and I'm going to divide it by the cos of 35. Okay, because remember, the cos of theta equals adjacent divided by hypotenuse. All I did was manipulate. Okay, so we'll take that number that we had there, divided by the cos of 35. Okay, we get our 329 newtons. Okay, everybody all right with that? All right, so what? I mean, there's like what, 2 calculations here, 3. This, find the force of gravity, divide it by 2, do a trig calculation, right? But there's intuitive steps. All right, now if we're talking about an intuitive question, this one's intuitive. You have to read it really carefully. The math is minimal, like extraordinarily minimal, okay? But there's a lot of intuitive things and careful reading that have to go on here, okay? So we've got a fish being reeled in by a fisherman. The fishing line is at an angle of 45 degrees, okay? Friction is opposing the motion with a force of 80 newtons. The fish is moving horizontally at a constant speed of 0.85 meters per second. What's the tension in the line? Okay, so if we're looking at that situation, okay, we've got our fish. I won't even draw a box this time. I'll actually attempt to draw fish. That's the line. Okay, so this angle here is 45 degrees. Okay, we're trying to find the tension in the line. We know the fish is moving horizontally at a constant speed of 0.85 meters per second. Okay, we also know that there's a force of friction acting backwards, okay, of 80 newtons. We need to find the tension in the line. Right? I'll give you a few minutes on that. Actually, before I give you a few minutes on that, if I was underlining key points in this question, what would I underline?
Constant speed.
Yep. That's the most important part of that question. Constant speed. I would also say that horizontally is equally, well, almost equally important, but the fact that it's moving horizontally is pretty important. Okay, but moving horizontally at a constant speed. Okay, I'm not even underlining the 0.85, am I? Spoiler alert, that might mean it's not important. Okay, give me a few minutes. Okay, your net force is 0 because your acceleration is 0. You have an 80 Newton force acting backwards, and the net force is 0. Think about what that means for your forward force. Okay, let's have a look at this. We've got a line here that's pulling on the fish. It's pulling it this direction. Okay, that means it's pulling, guys. It means it's pulling horizontally as well as vertically. But the question specifically says the fish is moving horizontally. Okay? If the fish is moving horizontally, then this upward force and this downward force that's always present do what to each other? They cancel each other out. Okay. How big is this horizontal force? 80 newtons. Okay, so I'm getting a few of those crooked looks again. Okay, what's the net force here?
0.
Okay, we just established that the upward force and the downward force cancel each other out. If the net force is 0, that means the horizontal forces also cancel each other out. If you got 80 newtons backwards, you have to have 80 newtons forwards. Now all you have to do is a trig calculation to get the hypotenuse of this triangle. That's the tension in the line. Okay, again, mathematically, there's one operation you have to do here. Is there a lot of intuitive reasoning that went on before we got there? Yeah. Okay, have to read the question carefully. Have to understand there's no acceleration, there's no net force. All the forces cancel out. Forces forward and backward are equal. Oh, now I have a forward force. Now I can use it to do this. Okay, a lot of little steps there. Okay, a lot of things to think about. So to get the tension, we're going to take the adjacent side. 80 newtons. We're going to divide that by the cos of 45, or the sine of 45. It doesn't matter because 45-degree angle means the two sides are what? Equal. Okay, but you should use cos because we're using the adjacent side. Okay, so when we do that, okay, we'll have the cos of 45, or sorry, not, we're going to have 80 divided by the cos of 45. All right, which gives us 113 newtons, 45 degrees above the horizontal. Okay, lots of little vector things to think about, lots of little things. Okay. All right, this is a little bit different. The math of it's also fairly straightforward, but there's no angles or anything to think about on this one. All right, so two workers are pushing a large crate across a level floor. One of them pushes with 300, the other with 250 newtons. Friction is opposing with 175. So all the forces are horizontal. They're all collinear. Okay, so that part, getting the net force should be straightforward. Okay, they're telling us the crate's accelerating at 1.57 meters per second squared. We're looking for the mass of the crate. Yeah, no, you've got it because the answer's right there. Okay, so we've got our crate. Okay, the crate's on the floor because it says they're pushing it across a level floor. Okay, one of the workers is pushing with 250 newtons. One of them is pushing with 300 newtons. Friction is opposing with 175 newtons. Okay, we don't know the mass of the crate. What can I find with those three numbers? I can find F net using the vector sum of all forces. All right, so F net will be 250 plus 300, which is 550, okay, minus 175, which would give us 400. It is 375, right?
Yes.
Yes. 375 newtons. There's my net force. Okay. The question also happens to tell me that the acceleration is 1.57 meters per second squared. Well, that's great because the other formula for F net is m times a. They gave me a. I just found out what F net is. I can calculate m. So the mass will be 375 divided by 1.57. Okay, that crate is 239 kilograms. Okay, everybody all right with that one? Okay. Now, this one, similar to the last one, except now instead of all the forces being collinear, now the forces will need to be added up using a vector diagram. Okay, so we're going to do some vector addition on this one. There's no friction, so your life got a little easier. Okay, there's no friction on this one. Okay, but there are two pushing forces that are not in the same direction. So, free body diagram, vector diagrams, vector sum of all forces go from there. Okay, we want the acceleration of the snowball. Okay, let's start this one out with just like the two diagrams and see how then I'll give you some more time on this one. So we've got the snowball. Okay, the snowball has a mass of 50 kilograms. Okay, it's being pushed in two different directions. One person is pushing with 130 newtons, 15 degrees west of north. Okay, so there's north. 15 degrees west of north would look like that. Okay, so we've got 130 newtons going that way. Okay, and then 110 newtons due west. That's my free body diagram. That's not going to help me answer the question. It's just going to help me to identify the forces. What do I need to do with those two forces? Draw them tail to head. Okay, if I'm pushing west and northwest, the ball is going to move this way, right? In a northwesterly direction. Probably more west than north, right? Because I've got a directly west force, and my other force is northwest, so it's going to be moving more west than north. All right, so what I'm going to do is draw my two forces in a vector diagram. So I'll have, okay, my 130 Newton force. It's got an x component, a y component. Okay, it's 15 degrees, and it's 130 newtons. My other force is 110 newtons due west. my net force then looks like that. Okay, give you some time on that one. Okay, so 1 year ago, this was the unit exam question. Okay, on force as a vector quantity. Okay, this exact question: a western force and a northwest force. Calculate the acceleration. Now, had I 2 weeks ago asked you this question, and instead of said newtons, said meters, calculate the displacement, how fast would you have done it? Exactly. Okay, you would have done it that quickly because you know how to do vector addition, and you're comfortable with it as long as it's in meters. Okay, as soon as I say it's forces in a rolling snowball, it's suddenly I don't know how to do that. Okay, but it's exactly the same. Force is a vector quantity, and we add all vector quantities in the same way. We put them tail to head. All that's extra on this is after I calculate the net force, I have to plug the net force into this formula. There's one extra step from what you would have done last unit if it was in meters. Okay, so I need to calculate, okay, x and y. So black x is the opposite side, so that'll be the sine of 15 times 130. Okay, so that's 33.646 newtons, and that's west. Okay, and then y is going to be the cos of 15 times 130. Okay, so 125.57. And that's north. Okay, now that I have those, now I can calculate what blue x and blue y are. Okay, blue y is easy because I only went north in one of the two parts. Okay, or only had a north directed force in one of the two parts. So y is going to be 125.57 newtons north. Okay, and x is going to be 33.646 plus 110. Okay, so we'll have 143.646 newtons west. All right, so now we've got our blue x and blue y. Can I calculate F net? Yeah, just use Pythagorean theorem. So F net, okay, will be the square root of our 125 with all the decimals obviously squared, okay, plus 143 with all the decimals squared. Okay, so okay, so we're looking at a net force of 190.794 newtons. All right, now that I have that, now I can calculate the acceleration. So I've got my net force, 190.794, and I divide that by the mass of the snowball, 50. When I do that, I should get 3.82 meters per second squared. But I'm not done because what did I not calculate? I didn't calculate the angle. All right, so I'm going to calculate theta, okay, because the angle of the net force and the angle of the acceleration are always the same, right? I mean, if I'm pushing something with 190 newtons in this direction, it has to accelerate in that direction. Okay, so theta will be the inverse tan of our opposite side, so 125 divided by our adjacent side, 143. Okay, and that's where we'll get our, actually, we'll get 41.2, right? Yeah, 41.2 degrees for this one. The way I drew it, okay? You'll get 41.2 degrees north of west. If you drew the triangle the other way, then you get the answer I had there, 48.8 degrees west of north. Okay, so there's how we do that. Everybody okay with that? Okay, vector sum of all forces, we know how to add vectors. It gives us our solution there. Okay, so this one, mathematically again, very easy, but it's asking you to calculate one of the forces involved and actually making you work backwards from the way we've been doing this. It's still the same steps, but instead of doing the vector sum of all forces first, I'm going to do it second. I'm going to do F equals m times A first. Okay, so give that one a try. Give you a few minutes. Okay, guys, this question is simple in that there's only one force acting on the curling rock, and it's friction. It says it's sliding down the ice. It didn't say anyone's pushing it. It's just sliding. It's slowing down, which is due to friction. Okay, it's due to friction. So all we have is a curling rock, okay, that has a mass of 12 kilograms being acted upon by the force of friction. Since this is my free body diagram, I only have one force, it's by default the F net. That's vector sum of all forces right there. This one, that's the net force. There aren't any others. Okay, so F net equals the force of friction, which equals mass times acceleration. Okay, so all I have to do is take 12 and multiply it by the acceleration, negative 1.12 meters per second squared. Okay, this should really have a direction on it. It should be backwards or negative. The question actually gave me negative, so my answer should be negative 13.4 newtons. Okay, easy to overthink a question. Okay? I mean, truly, if I wanted to draw an actual free body diagram of this, I would go, all right, force of gravity, normal force, but why didn't I bother? They cancel each other out anyway, so there's no point in drawing them. They don't add up to the net force. Okay?
was right. You said you added them.
And
How did that even?
okay, we did one like this earlier. See if you remember how to do it. It's like our lab tomorrow. Okay? So one mass is hanging over the pulley. One mass is on the table, but this time there is a small frictional force acting on the mass, on mass 2. Okay? The one that's sitting on the table. All right? See if you can find the acceleration of that one. And then we'll call it the day after that one. Okay, let's have a look at this one. So, the forces that are acting in this system are that we have a force of gravity. Listening, please. We have a force of gravity acting down on mass 1. Okay, its mass is 6 kilograms. All right, so we got 6 times 9.81. Right, so our force downward is 58.86 newtons. And then we have a force of friction that's resisting here on mass 2, okay? And it says that it's only 4 newtons, so it's pretty small by comparison. Everybody okay with that? Is gravity acting on mass 2? It is, but it's pulling it into the table, and what's the table doing? Pushing back, so it doesn't matter. Okay? Those are the only two forces that are contributing to the movement or acceleration of this system. So if I want to calculate the acceleration, then I need to know what F net is, and I need to know what the mass of the system is. Even though it wants to know the acceleration of mass 1, I need to calculate the acceleration of the system because it's the same. All right, so F net, very simply, is just going to be 58.86 minus 4. Okay, even though they're over a pulley, they're opposing each other. So our net force is 54.86 newtons. Okay, so now we can calculate the acceleration, 54.86 newtons divided by the combined mass of the system, which is 10.5 kilograms. Right, which is why we get...
No, dude.
Yeah, 10.5, yeah. Okay, so 54.86 divided by 10.5. So 5.2 meters per second squared, but it asks for the acceleration of mass 1, which is downwards. I have to put down on there. It's not on my answer here on the key, but it should be, okay, down, because that's the direction that one's going. Now, you're going to have a quiz tomorrow, and it's going to be on some questions like this. Expect some vector-related Newton's second law questions for your quiz. Then we're going to be doing a lab, so be ready for that. You're going to need that SparkView app again for tomorrow or the lab. Okay?